In this video, we're going to talk about how to do arithmetic with vectors. And in particular, we're going to talk about how to add vectors together, how to subtract them, and how to scale them. We're also going to talk about some applications of addition, subtraction, and vector scaling. And we're going to talk about the length of a vector and the formula for calculating that length. That length of a vector will also lead into the idea of a unit vector. To set the stage and to explain why vector addition is a thing that we would want to do, consider the following scenario. We've got two friends working together to push a desk. Now the first friend is exerting a force on the desk with a positive x component and a negative y component. So the first friend is pushing it in the forward and down direction. Now the second friend is exerting a force on this desk, which can be expressed by the vector 2, positive 1. So they're pushing it in the positive x direction, but they're pushing it slightly upward. Now physically, we can get a sense that these two friends working together are going to exert a combined force on the desk. Both of them are pushing the desk in the positive x direction, so their combined force will probably be in the positive x direction. But since one is pushing the desk down and one is pushing the desk up, their efforts will probably cancel each other out, and as a result the desk is probably not going to move at all in the vertical direction. Vector addition gives us a way to take that intuition about a real-world force or combination of forces and express that mathematically. Vector addition is used to represent things like a combination of multiple forces, as in the previous example. It can also be used to represent a combination of multiple velocities. For example, if you've got an airplane flying in the sky, and it has a velocity independent of any wind or air movement that's happening in the sky. But if you have a wind that's going against the direction of the plane, then the velocity of that wind will combine with the velocity of the plane to impede the plane's movement slightly and slow it down. Vector addition can also be used to analyze that situation. Now yesterday we also saw that vectors can be used to represent straight line travel, and vector addition in that context represents taking one path and then taking another. So a concatenation of two different paths. If you followed one vector and then followed another, where would you finally end up as a result of those two things? Now the beautiful thing about vector addition is that the calculation of the sum of two vectors is very, very simple. If you know the components of both of your vectors, then you can add the vectors component-wise. What it means is that you can add the x components individually and then separately add the y components together and then separately add the z components together. Add the x components, then the y components, and then the z components. To see how lovely this is, let's practice adding the vectors 0, 3, 4 and the vector 2, -1, 4. So if I wanted to sum together these two vectors, then I can individually and separately sum together the x components, the y components, and the z components. So our two x components are 0 and 2. Our two y components are 3 and -1. Our two z components are 4 and 4. And therefore the sum of these vectors is 2 in the first component, 2 in the y component, and 8 in the z component. Now to roll back to the example that we had about two forces being combined, about two friends pushing against a desk at the same time, we have the physics definition net force. And a net force is just a force that results from a combination of multiple other forces. The beautiful thing about net force is that it can be calculated simply using vector addition. So if we have force number 1 being exerted by friend number 1, so I'll call it F sub 1 with the vector arrow equals 1 minus 1. And we have friend number 2 exerting force number 2 expressed in components as 2, 1. What vector represents the net force that they're exerting on the desk together? Their combined efforts can be represented by the sum. The x component is 1 plus 2, result 3, and the y component is negative 1 plus 1, result 0. This is the net force. And this confirms our intuition that these two people working together will successfully push the desk in the positive x direction, but the force that they are exerting in the y direction cancels out. Now, as soon as you have addition of vectors, you have subtraction of vectors, because subtraction is just addition backward. And just like addition, vectors can be subtracted component-wise. Subtract the y components and subtract the z components separately. As a quick example, suppose we wanted to take the vector 3, 1, 5 and subtract the vector negative 2, 9, 7. To find the result, I would take the x components and subtract those. 3 take away negative 2. I would take the y components and subtract those. 1 take away 9. And I would take the z components and subtract those. 5 take away 7. 3 people this time are pushing a block. Now the first person is exerting a force which can be expressed in components as 1, 3. The second person is exerting a force which can be expressed as minus 1, 1. But who knows what this third person is doing? They're exerting an unknown force on the block. So I will just call their force vector angle bracket A, comma B. Now we do know that the net force exerted on the block as a result of all 3 people is equal to 0, 0. So in other words, all 3 of these people working together are exactly canceling out everybody's contribution. So the question is, what on earth is this third person doing to completely cancel out the work of the first 2 friends? To determine that, we can go ahead and we can do some vector subtraction. If I want to figure out F3, if I want to isolate F3, then I can subtract F1 and F2 from both sides, giving me 0, 0, take away F1, take away F2. So the third person's force is equal to 0, 0, take away 1, 3, take away negative 1, 1. So let's do that subtraction component-wise. The x component is equal to the first x, take away the second x, take away the third x. And the y component is equal to the first y, take away the second y, take away the third y. So this is the primary application of vector subtraction. Vector subtraction is used to undo vector addition, usually as a way of solving equations that contain vectors. Okay, I was about to go on a long tangent about MATLAB. MATLAB is some computerized software that is used pretty often especially in the physics and engineering areas. And one of the nice things about vectors, as combined with a computerized system such as MATLAB, is that it is a way of doing a list of calculations without having to use a for loop. Basically, if you need to add together a list of different items, you can put all of those items into a vector, add the vectors together, and because of the way vectors are added, it will add together all the items in the list. It's extremely effective and efficient from a computational point of view. Now we've added vectors together, we've subtracted vectors from one another. The third piece of vector arithmetic that we will be covering in today's material is vector scaling. And when we refer to scaling a vector, what we're talking about is taking that vector and either stretching it out or making it shorter. Vectors can be scaled, stretched, or contracted by multiplying the vector by a number. And this is also done component-wise. So in other words, if you want to take a number c, no arrow, and multiply it by a vector v with an arrow, you can multiply the components of v one at a time. Now let's see what effect different scalars, what effect different values of c have on the appearance and the properties of the vector v. For example, let's start with the vector v equals 2, 4. Let's calculate and list the vectors v, 2 times v, 1/2 times v, -1 times v, and -2 times v. Then let's draw each of these vectors and let's see what we notice about the drawings. Okay. So to begin with, we have our original vector v, which is equal to 2, 4. Now someone says, draw the vector 2 times v. So let's start by finding the components of that vector by scaling that vector component-wise. So the x component is doubled and it becomes 4. The y component is also doubled and it becomes 8. So if I draw a vector from the origin to that terminal point, that is the vector 2 times v. If I multiply each individual component by the number 1/2, 1/2 times 2 becomes 1. 1/2 times 4 becomes 2. This is the vector 1/2 times v. Negative v, where we're taking the negative of the vector 2, 4. So we can take the negative of 2 on the negative of 4. Then the vector points down and to the left, negative v. And then finally, let's work on the vector negative 2v. Negative 2 times 2, 4, which is equal to negative 4, negative 8. Okay, so let's compare some of our vectors here. We had our original vector, which was equal to v. When we multiplied it by 2, the vector pointed in the same direction, but it was extended so that it was twice as long. Whereas if we multiplied it by 1/2, it still pointed to the top right, but this time it was only half the length that it was before. However, when we started multiplying the vector by negative scalars, for example, when we multiplied by -1, the vector flipped so that all of a sudden it was pointing in the opposite direction. No longer top right, but this time bottom left. And if you multiplied it by -2, if you multiplied it by a negative large number, not only did the vector swap direction, but at the same time it also became twice as long. So takeaways here. One is that multiplying by a positive c gives you a vector with the same direction that you started with. So it preserves the direction, it keeps it the same. But if you multiply by a negative scalar, if you multiply by a negative number c, then that changes the direction of the vector so that the result points in the opposite direction. Additionally, if the number that you used for your scaling was relatively big in magnitude, something like 2, something like -2, then that caused the length of the vector to become larger. But if you multiply by something that's relatively small in magnitude, such as 1/2, then the vector shrinks as a result of that scaling. So as you might be able to imagine, in the land of computers, vectors also give you a really convenient way to increase or decrease the size of something. If you can represent something by a vector, and you want to scale it up or scale it down, all you have to do is take that vector and multiply it by a corresponding number, a number of an appropriate size. Now I want to draw our attention to a special situation of scaling and adding vectors, where we're scaling and adding together these very special 3 vectors, which are called I, J, and K. I, J, and K are used specifically for these vectors only. The vector I is the 3D vector where you have 1 in the x component and the rest are zeros. J has 1 in the y component, the rest are zeros, and K has 1 in the z component and everything else is a 0. These vectors are given the name the standard basis vectors for R3, where R3 is shorthand for 3-dimensional space. Now let's do a calculation of the following combination of the standard basis vectors. Someone gives me 3 times I plus 2 times j plus 7 times k. So let's go ahead and do 3 times 1, 0, 0 plus 2 times 0, 1, 0 plus 7 times 0, 0, 1. As always, PEMDAS still applies, so we need to scale before we add anything together. So I have 3, 0, 0, 3 times 1 being 3, 3 times 0 is 0. Likewise, we have 0, 2, 0. And likewise, we have 0, 0, 7. Now 3 plus 0 plus 0 is just 3. 0 plus 2 plus 0 is just 2. 0 plus 0 plus 7 is just 7. So what's interesting about this? What's interesting about this is that the scalar on I became exactly the same thing as the x component. The scalar on j became exactly the same thing as the y component. And the scalar on k became exactly the same thing as the z component. So the standard basis vectors give an alternative way to symbolically represent the vector ABC in angle brackets. You can write it this way in the angle brackets, or you can write it as the number A scaling the standard basis vector I, the number B scaling the standard basis vector J, and the number C scaling the standard basis vector K. Now, I will be the first one to admit that as a mathematician, as a math major, I am not particularly fond of this notation. But I will say that if you do take a science class such as physics or engineering, this is the notation that's most common there. Now, conspicuously, arithmetic operations that we have not discussed are multiplication and division. So the question is, can we multiply a vector by a vector? We scaled vectors, we multiplied them by numbers, but is it possible to multiply a vector by another vector? And the answer to that question is kind of. There is a way to multiply two vectors together, but it's not component-wise. And the reason for this is simply that multiplying vectors together component-wise is just not useful. There is no reason for us to do such a thing in any application. Now, we will have two so-called products, two so-called formulas for the multiplication of vectors that actually are useful and have some purpose in actual physical applications. Those are called the dot product and the cross product, and those will be coming up in the next 2 days. Now, when we are describing the relationship between two vectors, there are a couple of words that will come up pretty often. And the first word is parallel. Two vectors are parallel if one is a scalar of the other. In other words, one of your vectors is equal to some number c times the other vector. Another piece of terminology that comes up is two vectors point in the same direction if one is a positive scaled version of the other. In other words, it's not enough just that one vector is c times the other vector. That scalar has to be a positive number. Quickly scrolling back up to this exercise, we started with the vector v equals 2 times v. All these other scalar multiples of v would be considered parallel to the original vector v. However, only the vectors with a positive scalar, such as 2v and 1/2 v, are pointing in the same direction as the original vector v. So one of the things worth noting is that parallel vectors either point in exactly the same direction or they point in opposite directions. They point in the same direction if one is a positive scalar multiple of the other. In opposite directions if one is a negative scalar multiple of the other. So as a quick exercise, let's consider the following collection of vectors. We've got 1, 3, 2, 3, 9, 6, -1, -3, -2, and -1, +3, -2. So the question is, of these vectors, which are parallel And of those, which point in exactly the same direction rather than in opposite directions. Now the thing that strikes me is that if I take 3, 9, 6, that's exactly the same thing as 3 times the vector 1, 3, 2. And likewise, this third vector, where all the components are negative, is just the negative of 1, 3, 2. However, if I scale -1, +3, -2, I will never be able to get that scaled version of that vector to equal any of the first 3 vectors, because the signs in the fourth vector don't work out. The signs in the first 3 vectors are always the same for all 3 components, whereas vector number 4 has a change in the y component. It's the opposite sign of the x and z components. As a result, I can say that 3, 9, 6, 1, 3, 2, and -1, -3, -2 are all parallel. They are all scalar multiples of each other. However, only the pair 3, 9, 6 and 1, 3, 2 point in the same direction. The vector -1, -3, -2 is not included in this list because it's a negative scalar multiple of 1, 3, 2. Now, when we are given a vector in terms of its components, we will often need to calculate the vector's length. And for a vector v with the arrow on top, we have specific notation to refer to the length. The length is denoted absolute value symbols with the vector in between, or sometimes you may also see 2 absolute value symbols. I see both of these versions of the notation used pretty often. Now, in the previous video, we actually practiced calculating the length of a vector using the distance formulas in 2D and 3-dimensional space. It always worked out to be exactly the same thing as if we took the components, squared them, added them together, and then took the square root of the result. So for a 2D vector with components a, b, the length of that vector, the magnitude, is equal to the square root of a squared plus b squared. So I could represent this as the vector AB surrounded by absolute value symbols, or I could represent it as the vector AB surrounded by double absolute value symbols. Similarly, we saw that for 3-dimensional vectors, so let's say ABC, the length of that vector could similarly be found by adding together a squared, b squared, and c squared, and then taking the square root of the result. That was just a result of the 3-dimensional distance formula. As a quick example, let's find the length of the vector 3, 1, -2. In order to calculate that length, all that I need to do is take the square root of the sum of the squares of the components. So we have 9 plus 1 plus 4, that's 14. The length of this particular vector is the square root of 14 units. Which brings us to a concept called a unit vector. A unit vector is a vector whose length is 1 unit. The upshot of unit vectors is that they give you a convenient way of describing a direction to someone. If you care only about the direction and you don't care about the length at all, you can say, whatever, let's just let the length be a really simple number. Let's let the length be the number 1, and I'll use a vector of length 1 pointing in a direction to communicate that direction to the other person. This is super convenient in 3 dimensions especially, where it can be pretty complicated to describe a direction to someone, since you need a minimum of 2 angles, one for your horizontal orientation and one for an up-down orientation. Much more convenient in 3 dimensions to describe a direction by basically just pointing your finger in the direction. Now, let's practice calculating a couple of unit vectors. In the first exercise, let's find a unit vector with an angle of 3 pi over 4. So, of course, it's still implied that this vector must be 2-dimensional because we're only given a single angle, theta equals 3 pi over 4. And we're also told that this vector needs to be a unit vector, so the vector's length is given by r equals 1 units. Now we had a formula yesterday for a vector with a specified angle with a specified length, which was r cos of the given angle, r sine of the given angle. For a unit vector, the r is equal to 1, since a unit vector by definition has 1 unit length. And our theta was given to us as 3 pi over 4, which means that we're in quadrant 2 and cosine is negative, negative 1 over root 2, and sine is positive. Related question. Find a unit vector with the same direction as 5, 4, 1. Now, if we need a vector in the same direction as 5, 4, 1, then we need to multiply 5, 4, 1 by a positive scalar. So here is our idea. 5, 4, 1 already has some length to it. So take the inverse of that length, take the inverse of the length of the vector and then use that to scale the vector. In some sense, we're dividing out the length that the vector already has in order to create a vector of length 1. So the length of 5, 4, 1 is 5 squared, 25, plus 4 squared, 16, plus 1 squared. So that seems like 42, if I recall correctly. So I'm going to scale this vector by the inverse of 42. That gives me 5 over root 42, 4 over root 42, 1 over root 42. This vector definitely has the same direction as the one that we started with because it is a positive scalar multiple of the vector that we started with. And we can confirm that this vector that we obtained really is a unit vector. Now, this same process that we used in this exercise can be used in any similar exercise. If you want a unit vector in the same direction as any arbitrary vector v, then you can do that by taking the vector that you were given and then scaling that by the inverse of the vector's length. For simplicity's sake, you will also see this written as v divided by its length. So go through one component at a time and divide each individual component by the number which is equal to the length of the vector v. This will always work out to be a vector of length 1 because you are basically dividing away whatever length v originally had. So that concludes the material for today. We talked about vectors, we talked about adding, subtracting, and scaling vectors, and why such a process might be useful. Then we talked about the length of a vector, how to calculate it, and how to manufacture vectors of a specific length, in particular how to manufacture vectors of length 1.